Welcome to today's Explainer. I am absolutely thrilled you're here because we're looking at one of the most exciting shifts happening in technology right now, and specifically, exactly how it all works under the hood. Now, if you've used a chatbot recently, you're already familiar with generative AI. It's incredibly helpful, sure, but it's also entirely reactive. It just sits there, waiting for you to tell it what to do. But what if we took that same underlying intelligence and made it proactive? Well, that is the fascinating world of agentic AI. Okay, let's take a quick look at our roadmap for today. We'll start with generative versus agentic AI, then move into the agentic reasoning loop, cover the four types of memory, look at skills and connections, and finally wrap up with multi-agent mission control. Let's dive right in. First up, Section 1, Generative versus Agentic AI. You see, generative AI is essentially just a highly sophisticated pattern matching machine. You give it a prompt, it generates a response based on its training data, and then it just stops, right? Its job absolutely ends at generation. But agentic AI, that's a whole different ballgame. It's proactive. It takes your initial prompt and autonomously pursues it as a multi-step goal. It doesn't just spit out text, it actively makes decisions, orchestrates tasks, and takes actions in digital environments with barely any human intervention. It takes AI from being a simple tool to an active participant. Moving right along to Section 2, the agentic reasoning loop. So, how exactly does it pull off these complex tasks? Well, agentic systems use this continuous internal reasoning loop. First, the agent perceives its environment. Next, using specialized large reasoning models trained for logic, it generates what we call a chain of thought. It is literally reasoning through the problem step by step, kind of like an internal scratchpad to map out contingencies before it even makes a move. Third, it acts on that plan. And finally, it observes the results of that action before looping right back around. This continuous cycle is what lets an agent act as, say, your personal DevOps engineer, analyzing system logs, spinning up server containers to test fixes, and monitoring the results all on its own. Which brings us to Section 3, the four types of memory. But here's the thing, reasoning alone just isn't enough. If an agent can't remember anything, it's going to make the exact same mistakes over and over again. To prevent this, an agent needs memory. Researchers at Princeton developed frameworks like Koala, which breaks an agent's memory down into four categories that honestly look a lot like human cognition. First is working memory. This is the context window, exactly like a computer's RAM, super fast, but completely volatile once the session ends. Second, semantic memory acts as a persistent knowledge base for core facts and rules. Third, procedural memory holds learned skills, the how-to stuff. And finally, episodic memory keeps distilled insights from past experiences, so the agent actually learns and adapts over time instead of constantly starting from scratch. A really perfect example of that semantic memory in the real world is the agents.md file. It's just a simple markdown text file sitting at the root of a developer's project. Every single time an agent boots up in that specific codebase, it reads this file first. It gets all the persistent project knowledge, like exactly what testing commands to run, or how pull request titles absolutely must be formatted for that specific team. Basically, it stops the AI from flying blind and making rookie formatting mistakes. All right, let's jump to Section 4, Skills and Standardized Connections. So we've got a brain and a memory. Now the agent needs limbs to reach outside of itself and use external tools. Think back to that procedural memory we just talked about. If an agent loads every single skill it knows into its working memory all at once, it would completely overload its context window. To handle this elegantly, agents use skill.md files to practice progressive disclosure. The agent only sees a lightweight directory of what it can do. It's only when you actually ask for a specific task, like, say, building a PowerPoint deck, that the agent dynamically pulls in those exact step-by-step instructions. And what happens when the agent needs to go even further, reaching out to external databases or software platforms? It uses a brilliant open standard called MCP, or Model Context Protocol. Without MCP, developers would be stuck building a messy, custom API connector for every single external tool an agent touches. And that simply doesn't scale. MCP provides a universal, standardized interface, effectively wrangling the Wild West of API integrations into one clean protocol. To put that into perspective, imagine asking your agent to prep for a big client meeting. By routing through an MCP server, the agent can securely reach out and grab specific customer interaction records right from Salesforce or a Notion workspace. The MCP handles all that complex authentication and data translation seamlessly in the background, so the agent gets that external context instantly, making its answers highly customized and totally accurate to your business data. And that leads us to our final part, Section 5, the multi-agent mission control. Sometimes one single agent, no matter how smart or well-connected it is, just isn't enough for the complex jobs we demand. When workflows require teamwork, we use the A-to-A, or agent-to-agent protocol. This is where things get wild. Every agent publishes an agent card describing exactly what it does. Other agents can literally read these cards to discover and delegate work. For example, a specialized procurement agent could negotiate a vendor contract and then use A-to-A to seamlessly hand off that finalized contract to a dedicated finance agent for spend approval. We're talking about entirely automated collaboration happening at machine speed. We can also scale things horizontally using subagents. Say your main agent needs to review a massive codebase with 500 individual files. Doing that all at once would absolutely crush its context window. Instead, the main agent just spawns dozens of child subagents to do the work in massive parallel processing. Each subagent runs in its own fresh, clean context window, executes its specific security check, and reports back a concise summary to the main agent. It is a massive multiplier for efficiency. But here is a really crucial point. Single agents are incredibly fast and capable, sure, but they harbor a massive systemic flaw. They hallucinate. And they do it with absolute, unwavering confidence. A solo agent doesn't have an internal uncertainty meter. It will feed you a completely fabricated answer with the exact same conviction as a stone-cold fact. Now, in low-stakes tasks, that's an annoyance. But in high-stakes environments, like medicine, finance, or legal compliance, confidence without verification isn't just a bug, it's a total liability. So, how do we solve this hallucination problem? Well, we have to ask ourselves, how can we design AI systems that emulate the exact redundancies we already rely on in human institutions? Basically, how do we bring the rigorous concept of a mission control right into our AI architecture? We actually don't have to reinvent the wheel here. We can look all the way back to the 1969 Apollo 11 moon landing as the ultimate blueprint. NASA didn't rely on one super genius to make every call. No way. They used a room full of intensely focused specialists, Guido, Fido, Ecom. They ran a strict go/no-go protocol requiring unanimous consensus. When that terrifying 12:02 computer alarm blared during the lunar descent, flight controller Steve Bales didn't just guess. He relied on a backroom expert, Jack Garman, to instantly verify the error was manageable. Literally no single person made a critical call without verification from the group. That, right there, is the definition of earned confidence. We can build a machine-speed version of this using multi-agent architecture. Think of it like a medical tumor board, where multiple doctors rigorously debate a diagnosis to ensure total accuracy. Instead of one agent giving an unchecked answer, we use a team. First, we have a generator agent that whips up a fast, creative first draft. Then we pair it with a verifier agent whose sole technical function is to cross-check citations and catch those confident hallucinations. And finally, we toss in an adversary agent to red team the output, actively trying to break the logic and find flaws. By structuring the system this way, we are forcing our AI to actually earn its confidence through rigorous cross-checking. So, I'll leave you with this final thought for today's explainer. As you start developing and deploying agentic AI in your own high-stakes projects, which path will you choose? Are you going to architect a collaborative society of agents built on rigorous verification and trust? Or will you let a confidently wrong single agent confidently drive your business right into a lake? The underlying technology is here, the protocols are standardizing rapidly, and honestly, the choice is entirely yours. Thanks so much for joining me today, and keep exploring.